Okay, in this video we are going to use the following information, IR and NMR, to propose a structure that's consistent with the analytical data. So we need to use this data to draw a structure that is accurate to the IR and NMR. Really, we have three pieces of information. We have our chemical formula, our IR spectrum, and then, not shown here at the bottom, our NMR. So we're going to use those three pieces of information to solve a structure. The first thing that we need to do is use our chemical formula. We're going to calculate double bond equivalents, DBEs, or also called the index of hydrogen deficiency, using a formula to do that. And the formula that we use is N plus 1 minus M divided by 2 plus T divided by 2. And that's the formula that we use to determine the number of double bonds or triple bonds and rings we have. In this formula, N equals the number of tetravalent atoms, carbon in our example. M is equal to the number of monovalent atoms, hydrogens and halogens, and T is equal to the number of trivalent atoms, which is nitrogen. Well, you'll notice here we don't have to consider divalent atoms like oxygen. So oxygen, divalent atoms are not in the formula. So filling out our formula, what we see is we have 7 carbons, 7 plus 1, and then we look at the number of hydrogens we have and halogens. In this case, that is 14, so minus 14 divided by 2. And when we do this problem, what we get is we have 1 DBE, or double bond equivalent. So our molecule either has 1 double bond or a ring associated with it. Now, next what we're going to do is look at the IR spectrum. So the first thing that we're going to do here is analyze the spectrum, and we'll start in zone 1. So looking in zone 1, we don't see any peaks at all, so there's nothing there, but that is some useful information, because what we really know here is that we don't have any OHs, so there are no OHs in here. Knowing that we do have oxygen in the molecule, we know that there are no OH bonds. Next, we're going to look at zone 2, and we see some peaks in zone 2. And what we like to do in zone 2, what I describe as drawing our 3000 line. So I'm drawing this orange line here, and you see it's a little bit to the right of 3000. There are no peaks immediately to the left of it, but we do have peaks to the right of that. Oops. And these peaks are going to represent sp3 carbon to hydrogen bonds. Moving forward, we get to zone 3. There's no peaks here, so no triple bonds. And then that brings us to zone 4, so clearly there's a peak here at about 1720 or 1730. And that's the biggest peak in the spectrum. And what we know is that clearly is a carbonyl. So this giant peak here is clearly a carbonyl peak. And what's important about this is we knew that we had 1 DBE, and we've now seen that 1 DBE, which is a carbonyl. Moving to zone 5, I don't have any carbon-carbon double bonds, and we can ignore everything in the fingerprint region below 15. So we've analyzed our IR, no OH peaks, sp3 carbon to hydrogen, and our carbonyl peak, which again we saw from our DBE. So now let's take a look and analyze our NMR and then finish solving our structure. Okay, so we are going to scroll down and take a look at our NMR spectrum now. What I want to do is keep in mind that we need to remember a couple things. So I'm just going to, on this side here, kind of write down a couple things that we've learned. And what we learned is we have a carbonyl somewhere. Okay, so we will just kind of put this information really over to the side of things that we need to remember. That was our 1 dBe. And then obviously we have sp3 carbon to hydrogen bonds in here as well. Okay, so looking at our NMR spectrum, let's count our number of signals. We have one signal here at 5, another signal about 2.3, another signal about 1.7, another signal about 1.2 or 1.3, and a signal about 1.8. And then we do see a little signal over here at 0. So just one thing I kind of want to point out to remember is remember that we use an internal standard many times when we're running our NMR, and that is TMS. So this peak that we see at 0, what we want to do is remember that we're not really going to look at that peak. That is our internal standard peak of TMS. So we don't have to worry about that peak there. So let's go ahead and label all of our peaks, starting left to right, and I like to use letters. So the first peak we will call A. Okay, we'll move over. Our next peak is B, followed by C. This big doublet here will be D, and finally we have a triplet that is going to be E. So we have 5 peaks. One thing you'll notice from our NMR spectrum is the splitting we can get by counting the number of peaks, and we'll do that in a second, but the integrals are not provided for us. So what we have to do is measure them. And if you remember, we have this red line that goes throughout the spectrum. That red line is really calculating the area under each of these curves. And the area under the curves represents how many hydrogens they are. So what I'm going to do is literally take a ruler and measure the height of the line throughout the peak. So I'm going to measure the height from here to here using a ruler. So if I take out a ruler and I measure this height, I see the height from here to here is actually 1 centimeter. So I'm going to write that down here. So we'll do our integrals in blue. So our height here was 1 centimeter. When I look at peak B, I'm going to measure the height from here to here. And that height comes out to be 2 centimeters. So we'll write that down. Looking at peak C, I'm going to measure now my height from here to here. And again, that comes out to be 2 centimeters. So we'll write that there. Looking at peak D, I'm going to measure the height from the bottom of our line here way up to the top there. So our height over the peak from here to here, that's representing the area. And using a ruler, that measures out to 6 centimeters. So we'll write that above the peak as 6. And then we're going to move over to our last peak, E, and we'll measure the height from here to here, the height of E, and when we measure that, we get a value of 3 centimeters. So what we've now done is actually measured out our relative integrals. So let's check these values here. Here I have a value of 1 to 2 to 2 to 6 to 3, and that's going to represent a ratio of our peaks. What we really need to do is make sure that corresponds to the number of hydrogens. Do we need to multiply that by a value? Do we need to divide it by something? So let's add these values up. 1 hydrogen plus 2 gives us 5, plus 6 is 11, plus 3 is 14. And if we remember from our formula, we had 14 hydrogens. So these values actually correspond to the number of hydrogens we have. The signal for A is represented of 1 hydrogen, B is 2, C is 2, 6, D is 6, and E is 3. Okay, so let's start assigning some structures here. So let's first start with A. So if I count the number of peaks I have 1, 2, 3, 4, 5, 6, 7. So looking at peak A, what we can do is talk about the number of peaks we have. 7 peaks makes this a septet. So let's write that information down. Here we have a septet. And let's go ahead and go through and do this for all of them before we actually assign our structures. Looking at B, B clearly has 3 peaks. So that makes B a triplet. Okay, so 2 comma T to say it's a triplet. If we count our peaks at C, we have 1, 2, 3, 4, 5, 6. So peak C has 6 peaks. So we can label that a sextet. Okay, so peak C is a sextet. Looking at D, that's easy to see. That's a doublet. So we can just abbreviate that with a D. And finally, looking at our peak E here, this is clearly a triplet. So let's come over to E and label that as such. E is a triplet. So again, looking at peak A, integral of 1, septet. B, integral of 2 and a triplet. C has an integral of 2 and is a sextet. D integrates to 6 and is a doublet. And E integrates to 3 and is a triplet. So now we have our full spectrum that we can work with, and we can go ahead and start assigning pieces. So I like to start from the thing that is furthest downfield. Alright, that means the peak with the highest number on the left. So we'll start our analysis really looking at A. Okay. So because A integrates to 1, we can say that this is a single hydrogen that is connected to a carbon atom, because there's 1 hydrogen, and that is a septet, meaning that is next to 6 hydrogens. Now obviously we can't put 6 hydrogens on 1 carbon. Okay, so if it's a septet, the n+1 rule says it's next to 6 hydrogens. We can't put that on 1 carbon, but we can put that on 2 carbons. So what that means is there are 2 carbons connecting to our singlet, and each of these carbons has 3 hydrogens on it. So connected to that peak A, I have 2 methyl groups. So let's draw those in here. And now clearly we see we have, for our peak A, I have 3 neighbors there, 3 neighbors here, and a total of 6 neighbors and 7 peaks. So what I like to do here is draw a little squiggly line, and that tells me that this is a piece I just made. So we're really done looking at peak A. Alright, so looking at our spectrum, I'm just going to kind of cross this off. We've evaluated that peak. Now notice I just drew in 2 methyl groups here and here. So let's find those in the spectrum. And this is an isopropyl group, right? What we're looking at here is an isopropyl group. So which of our peaks has an integral of 6? Easy to see, that's peak D. So the 2 hydrogens that I drew, or sorry, the 2 methyl groups that I drew here correspond to peak D. So we can label that as peak D. If we double check, this has an integral of 6 because we drew 6 hydrogens and it is a doublet, and that makes complete sense. 6 hydrogens here, they are adjacent to 1 hydrogen. They have 1 neighbor. So A and D is definitely a piece that we have. Okay, so let's move on. Now we'll take a look at our peak B. Okay, peak B here, integral of 2 and a triplet. So let's draw that out here. So peak B, we have 2 hydrogens connected to a carbon atom. And that is a triplet, so it has 2 neighbors. So let's draw those 2 neighbors in here. And that corresponds to B. So now B is done. And what we need to note here is I've just drawn 2 hydrogens. So B is done. And sorry, I didn't cross out D. Let's cross D out. So now I have a choice. So the 2 hydrogens that I drew in here can either be our triplet at E or C. Now, it's very clear to see, because I just drew in 2 hydrogens here, that it clearly cannot be peak E because E integrates to 3. So what we drew next to B, this peak here has to be peak C, because C has an integral of 2. So let's take a look at peak C now. Integral of 2. It's a sextet, which means it has 5 neighbors. So looking at C, to the left of it are 2 neighbors, so I need to draw 3 more neighbors. So let's draw those neighbors in. I'm going to draw another carbon, and that carbon is going to be connected to 3 hydrogens. Okay, so C is now done. We've analyzed C, and conveniently we only have 1 peak left, E. E integrates to 3 and is a triplet, and that's exactly what I just drew. So looking here, 3 hydrogens, so an integral of 3, and it's next to 2 neighbors making it a triplet. So this final piece is BCE, and that corresponds to a propyl group. So let's just draw in our connector here to show that that is a piece that must be connected to something. And now, looking at our NMR, we've analyzed all of our peaks. And by doing that, what we've done here is we really have 2 pieces from our NMR. We have our isopropyl group, consists of A and D, and we have our propyl group, which consists of B, C, and E. So what we need to do now is look at our chemical formula and find out what is missing. What atoms are we missing? Okay, so we know our formula, C7H14O2. So let's first count our carbons. So over here we have 3 carbons plus another 3 carbons. So we're actually missing 1 carbon atom. So we're missing a carbon atom. Okay. The other thing we're missing is we have 2 O's, so we are missing 2 oxygens. And now what we need to do is take these missing pieces, or take these missing atoms and turn them into pieces. And here's where we remember our IR. Our IR clearly showed that we have a carbonyl, so clearly these pieces are going to correspond to a, let's give ourselves a little more room here. These pieces are going to correspond to a carbonyl, and that carbonyl has 2 bonds associated with it, and then we still have a leftover oxygen. So let's draw that oxygen in, and of course that oxygen draws 2 bonds, or has 2 bonds as well. So here are 2 other pieces that we have. So now if we count our number of carbon atoms, we have 3 carbon atoms over here, another 3 carbon atoms, and then there's another one. So 7 carbon atoms. Count our hydrogens. Here we have 6, 7, plus another 2, 4, 7 gives us 14, and 2 oxygens. So every atom is now accounted for. Now that every atom is accounted for, we can try to put our pieces together. And how do we do that? Well, what we have to do is now see how these are connected. And there's really 2 possibilities. Our isopropyl group could be connected to our oxygen, which is connected to our carbonyl and our propyl group, or the isopropyl group could be connected to the carbonyl and the oxygen and then the propyl group. The 2 carbon pieces here are terminal pieces. They only form 1 connection, so those have to form at the end. The pieces we derived here have 2 connections, so those have to be connected together. So let's do that. Let's cross that out and show that clearly we have an O connected to a C double bond O. And both of these are now connected to something else. So now what we've done is shown that we only have 3 pieces. So now our decision is even easier. Is the isopropyl group connected to my oxygen, or is it connected to the carbonyl? And same for the propyl group. Now how do we decide what pieces are connected? What we have to do is look at the chemical shift of this peak A and the chemical shift of peak B and see what makes sense. Looking at the chemical shift of peak A, this has a value of 5. Okay, so that's pretty downfield. That's a high ppm number. Okay. If you look at the value of B, that comes at about 2.3, between the range of 2.3. Okay, so what we know is that carbon to hydrogen to O, C to H to O, normally comes between 3 and 4, and we don't have anything there. This peak at 5 is further downfield. It's a higher ppm number. The carbonyl, an H, so an H to a C to a carbonyl, that normally comes between 2 and 3, and we do have a peak there. So what this clearly indicates is B is not going to be connected to our O, it's going to be connected to our carbonyl. So what we can do is draw our final structure. What I'm going to do here is draw my isopropyl group. That isopropyl group is connected to our oxygen. That oxygen is of course connected to our carbonyl. and then we finally have a propyl group attached. Okay, so from our analysis, this is clearly in the top, our final structure.